let me ask you a very interesting logic problem known as the poison bottle problem on the internet. So the problem goes like this. There's a king who is hosting a ceremony or a party in his house or castle, and he has invited a lot of guests for that, and he has ordered 1,000 bottles of wine. And the party is exactly after 24 hours from now, but he gets information that one of those bottles is poison. So he has a lot of prisoners to execute, probably more than 1,000 prisoners, and he wants to test all those bottles on his prisoners so that he can actually take that poison bottle out of those 1,000 bottles, right? So the poison actually kills anybody in 20 hours, like even if he takes a single drop of it. So what is the minimum number of prisoners does he need in order to take that bottle out of those safe bottles, right? So you can think about this problem, and when you're done, you can come back to see the solution. You can pause it right now. So I assume you had a take at it. So the correct answer, or the minimum number of prisoners required in order to test 1,000 bottles to take out a poison bottle, is none other than 10. Well, I'm not kidding. It's surprising, I know, but it's how it works. You only need 10 prisoners in order to test 1,000 bottles. So let me explain how. First of all, you need to minimize the figures or simplify the figures in order to see how it may be achieved. So for example, you only have 3 prisoners, A, B, and C. So what do you think? How many bottles can be tested using only these 3 prisoners? Well, you can have a bottle that you can give to A, you can have a bottle that you can give to B, and you can have a bottle that you can give to C. And whoever dies, for example, B just died, then you know that bottle number 2 was poison. But is it only 3 bottles you can test from these 3 prisoners? No, you can have a bottle number 4 that you can give to A and B. So in case A and B die, both of them die, then that means bottle number 4 was poison. And there can be a bottle number 5 that you can give to A and C. And if A and C die and B survives, that means the bottle number 5 was poison. And then you can have a bottle number 6 that you can give to B and C. So that means you can have another bottle. So if B and C die, that means that bottle that you gave to B and C was poison. And then you can have another 7th bottle that you can give to all of these A, B, and C. So if all 3 of them die, that means the bottle number 7 was poison. So it's not about how many prisoners are there, or they have to drink one bottle or sample from one bottle each. You can have a lot of combinations from only these 3 prisoners, so that you can actually test a lot of bottles using minimum number of prisoners. So let me really check out for like 10 prisoners. How many bottles can you test for with the 10 prisoners? So if you only had one prisoner A, you can only have one bottle tested. If you had B, then you can test like 3 bottles. One you can give to A, one you can give to B, and one you can give to B and A. If you had C, you will have combinations like CA, CB, and CAB. And for example, if you had D, then D, DA, DB, DC, DAB, DAC, DCB, and guess what? DABC, right? So that's how you can have a lot of combinations with only 4 prisoners. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you can make a table. You can actually make a table where you can write number of prisoners and bottles tested, or bottles can be tested. So when the number of prisoner was 1, then you can only test 1 bottle, right? And when the number of prisoners were 2, you could test 3 bottles. With B and A, you could test 3 bottles, 1, 2, and 3. With number of prisoners 3, like when C was also introduced there, then 1, 2, 3, 4, 5, 6, 7, right? And with number of bottles 4, you could see that 8, 9, 10, 11, 12, 13, 14, 15. So you can see a pattern is made here. You are just adding +2, then +4, then +8. And if you just count for like number of bottles be 5, you would just see that you would just add 16 more, and 15 plus 16 is 31, and so on. That's how you can actually achieve to a general formula for number of prisoners and number of bottles, that is 2 to the x minus 1. So how does it work? You just need to put, if you put in 5 here, 2 to the power is 5 is 32 minus 1, that's 31. And if you put in 10 here, 2 to the power 10 minus 1, then you will have that number of bottles to be tested for 10 prisoners. But how do you actually really calculate anything like the number of prisoners from this formula? Like this formula really gives you the number of bottles tested, right? So you can further derive the formula for x, and then it becomes log of base 2 to the number of bottles plus 1. So you just need to put the number of bottles that are to be tested here, and you simply get the number of x, or what exactly x is, the number of prisoners required. That's x. So in this case here I have a calculator, and I'm just putting in where is it? Yeah, here, log 2 to the number of bottles tested, that is 1000 plus 1, that is 1. So it gives me an answer for x, that is 9.967, which is approximated to 10. So you need at least 10 prisoners in order to test for 1000 bottles. So with this formula you can actually really calculate for any number of bottles. For example, what could be how many prisoners do you need in order to test a million bottles? So you just need to go back here and you need to write in for million, and well, you need exactly 20 prisoners for million bottles. So I hope it made sense. It really involved a little bit of mathematics, but it was really logical. And if you really got fascinated by this problem, do share it with your friends and play your role in spreading the knowledge. So at the end, I just want to add a little bit of interesting fact or appreciation of mathematics and combinations and permutations and binomial expansion and Pascal triangle. I hope a lot of you have heard of Pascal's triangle. And how does Pascal triangle really forms from all these combinations that we made here. So first of all, with only one prisoner, you could only have one bottle tested, and with two prisoners, when you had two prisoner B and A, you had total of 3 combinations, but you had one combination with B only and one combination with B and A. And when C was introduced, you only had one combination for C alone, and then you had 2 combinations for 2 prisoners together, and then you had one combination for 3 prisoners together. And then when D was introduced, you had one combination for D, you had 3 combinations for two prisoners together, then you had 3 combinations 3 combinations for 2 prisoners together, and then 3 combinations for 3 prisoners together, and only one combination for 4 prisoners together. And for E, as you can see here, one combination only for 1 prisoner, and then you can see 4 combinations for 2 prisoners together, and then you can see 1, 2, 3, 4, 5, 6 combinations for 3 prisoners together, and then again 4 combinations for 4 prisoners together, and only one combination for 5 prisoners together. So this beautiful thing forming here is known as the Pascal's triangle. What is happening is that every two digits you are just putting in a row add up to the next one here. So 1 plus 1 is 2, or just you can see 2 plus 1 is 3, 2 plus 1 is 3, 3 plus 3 is 6, 1 plus 3 is 4, 1 plus 3 is 4, and the next row is gonna be 5, 10, 10, 5, 1, and so on. So I don't know how exactly Pascal triangle is involved or incorporating or really displaying its role in all these combinations, but it is really playing its role in binomial expansion and binomial series. Well, these are the coefficients of the binomial expansion. So that's a little bit of interesting fact, and and a little bit of appreciation for mathematics involved in solving all these logic problems. So I hope you really found it interesting.